Swayam Prabha. Digital India. Educated India.
All right. So, oh, you are still drawing? Okay. So, you have to imagine that, there are two atoms sitting here in between the two, these planes, right. So, you need to imagine that, and then if this is root 2a, of course, like this, and then this becomes root 3 by 2 times a is a lattice constant, a is a lattice constant, okay. So, it's a geometric relation, so you should be able to do that, all right. Okay. So, now, if you see here atomic arrangement, these atoms are closely packed, whereas these are somewhat, there are a lot of spaces here, and here there is a lot of space. So, this plane is little flexible, whereas, as we go from here to here, this becomes more rigid, more stable, more rigid, right. Okay. So, that's also an important thing which we need to notice. Now, these planes, suppose if I have a plane like this, there is a fourfold hollow site here, you see, this one. So, the adsorbent molecule which you are talking about can go and sit somewhere here. That may be the chemabsorption valve. That may be your chemabsorption valve. The potential energy is very, very low. So, the adsorbent molecule can go and sit in this place. This is in a fourfold site, or the adsorbent can go and sit on the top of one of the atoms. For example, carbon monoxide, if it is absorbing on platinum surface, so the CO will go and sit on one platinum, right? And then, for example, in case of oxygen, maybe it can split into oxygen atoms. This oxygen atom can go and sit in the here, somewhere here, in the fourfold site. So, this is on top site, fourfold site. You can have bridge sites also. Between the two atoms, there is a bridge site, twofold bridge site. The molecule can go and sit in the bridge site as well, right? Or you can have twofold bridge site and then fourfold hollow site here. This is a short bridge and this is a kind of a hollow fourfold site. Okay. So, this is a bridge actually, this is the bridge, this is a long bridge. This is not a long bridge, they are touching each other, long bridge can be there. So, all these sites are possible, and on these sites, if you adsorb, for example, a halogen molecule, halogen chlorine, it can dissociate into chlorine atom. The chlorine atom can go and sit in either on this site or in this site. This is a fourfold site, this is a threefold site, halo site. The chlorine can go and sit there. Okay. Similarly, for example, you take a alkene, for example, this alkene can form a bond with the metal, one of these metal atoms through its pi bond, and then giving rise to this kind of a pi complex. That's how it gets activated. What is actually catalyst and activation? Catalyst is nothing but it actually alters the bond, right? So, as a result, the molecule which is difficult to break can easily break and then react with some other fragment. That is the catalytic action basically. Okay. Suppose say hydrogen and oxygen if they don't come together, give you water, if the same will go and sit on a platinum surface, they break. You have hydrogen and oxygen. Then they react and give you water. Okay? The same thing if it has to happen in the gas phase, it doesn't happen. Activation energy is very high. Activation energy is nothing but again you break the bond and then make the product. So now this bond, which is a pi bond, can interact with the metal atom, forming a pi complex. It can also happen that this pi bond can completely break and then make a new bond with metal atoms here. That will give you a di-sigma adsorption. Di-sigma adsorption. Okay? And similarly here, if you see, this is a metal carbonyl. The carbon monoxide can interact with one single atom, or two atoms, or three atoms, or four atoms. This is you end up getting four different adsorption species here. How do you distinguish this? For example, here the CO, single, triple bond, double bond, single bond. So how do we analyze that? Any spectroscopy techniques we can apply? IR. Metal carbonyls, if you see metal carbonyl chemistry, the IR stretching frequency of this one and these are also different. Starting from all the way 2300 to it will go to all the way to 1200 centimeters. Metal carbonyls, in inorganic chemistry, you see the metal carbonyls. There, you can distinguish these. So similar species are also form on the surfaces. Okay. Similarly, for example, ammonia, there is a lone pair on nitrogen. This lone pair can interact with the metal and then give you this kind of a surface species. And then that can lead to further slowly decomposition of this. Okay. So these are all possibilities. On surface, adsorption sites are often different from catalytic active sites. These are adsorption sites. Adsorption site can be catalytically active, or it need not be also. So that's the reason why spectator site, active site. People are now talking about it will go and sit there, but it is only a spectator. But it will go and sit there, it will react and give you the product. Active site. Now that is the research which is now going on. To identify the species, is a spectator or is it actively involved in the reactivity? So you need to distinguish these two using in situ spectroscopy techniques. Okay. Okay, the another interesting phenomena that can happen on surfaces, particularly I am taking platinum, is a very well-known example. Suppose if you take platinum 100 plane, just now I showed you platinum 100 plane, atomic arrangement is something like this. The square geometry, there is fourfold symmetry. But then this surface, once you make, it is not stable. It immediately reconstructs to hexagonal geometry. So this happens on the surface. I have a platinum. Suppose I grow a single crystal of platinum and cut it in 100 plane, so I should get this geometry. But then that geometry is not stable. Even at room temperature or slightly high temperature, immediately it changes to this particular geometry, but only on the surface plane, surface one or two layers. Bulk will remain as it is. Only on the surface it changes. This is called reconstruction. Those days there was no way to analyze this, but nowadays it is possible to analyze all this. It is possible to analyze all these phenomena that which are happening on the surface. Right? To reconstruct a hexagonal plane, this energy is 40 kilojoules per mole, this is more stable compared to this one. You see here, as I showed you here, this is more rigid compared to this. Right? So what is this going is going from here to here, more rigid. surface, more rigid surface, right? Now, if you take platinum 110, don't worry about this is a kind of a notation. Don't worry about this one by one. But what the platinum 110 has this plane. You see that? This one, this plane. Platinum 110. You have rows of atoms which are separated. 1 row, 2, 3, 4 rows, but the rows are not touching. The rows are not touching. So these are rows here, you see. Now, when you make this surface, the platinum 110 surface, the surface atoms, immediately reconstruct and give you a reconstructed surface like this. You see here, there is one. You remove one of the row here, alternate rows, you get this one. So one row is missing. One row is missing. So this phenomenon is also observed on platinum surface. And also there are other metals. There are other metals where one row is fully missing. So this surface is more stable. This surface is more stable. Okay? Come to platinum 111. Platinum 111, as I told you, is hexagonal symmetry. See, hexagon is surrounded by 6 atoms, right? This is hexagon. And this one does not undergo any reconstruction. It is already hexagonal. It does not undergo any reconstruction. Okay? This is called reconstruction of surface reconstructions observed on platinum. There are many metals. If you have a single crystal, all these things are observed. How do we study them? We study them using what is called scanning tunneling microscope and low energy electron diffraction. Scanning tunneling microscope and low energy electron diffraction methods. Scanning tunneling microscope and low energy electron diffraction method, which I don't think I have time to talk to you, but these are the two methods which can be studied, which can be used to study these reconstructions. Okay? Scanning tunneling microscope and low energy electron diffraction. Low energy electron diffraction. You have X-ray diffraction, no? Similarly, you have electron diffraction, neutron diffraction, right? Okay? Okay, all right. Okay. So as I said, so I just gave you the background of why is it important. The surface atomic arrangements, reconstructions, these are all very important, particularly for catalytic reactions. Now I will show you an example here. The landmark of hydrogen catalysis and surface chemistry is ammonia synthesis. Ammonia synthesis, right? Now, lot of ammonia is used for fertilizers, and then there are many other applications here, fertilizers, explosives, and etc. They are also used for nitric acid, amines, nitriles, nylon, organic nitrogen compounds. These are all industrial uses of ammonia, right? So this is mostly this ammonia production is from the nitrogen from the air, nitrogen from air. So the process is called Haber-Bosch process, invented in 1908, and then Fritz Haber is the one who actually worked in this area. This is almost more than 100 years old. Everybody was very happy. Why is it Haber process so important? It makes ammonia. Why ammonia is important? The population, today's population is, what is world population? Population means human beings. We don't consider other things, but how many human beings are there on the planet? In billions. How many? What is the population of India? You should read newspapers once in a while. 1.4 billions. Indians are 1.4 billions. right? Or otherwise 140 crores, right? In the world population is about 7.5 to 8 billions. 7.5 to 8 billions. All these 7.5, 8 billion people have to have breakfast, lunch, dinner. That much of food is required, right? That much of food is required. That we are growing that much of food from the planet Earth. Huh? If you want to have food, then you have to go say namaskara to our farmer brothers and sisters, right? They are the ones who are growing food for us. Obviously, imagine all of them. 1 year they don't do anything. They will not grow food. That's all. We will not have breakfast, lunch, dinner, right? For them to grow, for plant growth, ammonia is important. Ammonia is converted to nitrate fertilizers, urea, etc., and those are the ones which they are using for plant growth, right? So, as a fertilizer, this is very, very important. And then actually this Haber process, ammonia synthesis, is the one which is actually feeding the people of the world, right? Now the question here is, it is a very intensive process, energy intensive process. It requires 300 degrees centigrade, 1 megapascal pressure to apply to convert nitrogen and hydrogen to ammonia. Delta G should be for this. What should be the delta G? Delta G should be negative. Delta G should be negative. But you react, put them together, you will not get ammonia. You have to have catalyst, iron catalyst, which also contains some potassium, aluminum, cobalt oxides. And these are the ones, this iron is a catalyst actually, these are all some kind of promoters. And then at this temperature, you are under the influence of this catalyst, this react will give you ammonia. Right? This is a very energy intensive process. Now, the research is going on in our department and in many places, converting nitrogen to ammonia at room temperature, ambient conditions. Ambient conditions. You see how much energy you will save. How much energy you will save, a lot of energy. So this is one of the important research areas that is going on in across in India, many labs, other places also. The potentially a Nobel Prize winning problem. If somebody can actually bring out, decrease this temperature 300 to even 100 degrees, and then room temperature, and then or 100 or less than 100 degrees centigrade, and then less pressure. Potentially, it is a very interesting or a very important problem that people are working on. Okay. Now, this reaction was basically invented by Fritz Haber. Why did he do that? Because people were starving for food. So he started working and then got this one ready and then made it as an industrial process. It's an equilibrium reaction. You see this? This is an equilibrium reaction. It will come back here. So that is the reason why to drive this equilibrium towards the right, people once ammonia forms, they remove ammonia. Once they remove ammonia, Lee-Chatelet principle tells you that reaction will go from this direction to this direction. Okay? Lee-Chatelet principle, are you able to recall that? External factors like pressure, temperature, how does the equilibrium get shifted? Right? So in 1908, Fritz Haber, BASF is the company, Haber, they entered into agreement to work towards industrial scale production of ammonia. And then the next 5 years, they actually developed this into an industrial process. In 1903, first commercial plant was started with 300 tons of ammonia per day production. 1913. 1913, none of us were there. Even today, these plants are there everywhere. In India also, there are a few places these plants are there. And they use iron. Iron is the cheapest one. Of course, ruthenium can be used, osmium can be used. Osmium is toxic. Ruthenium can be used. Ruthenium is expensive. So iron is the cheapest one, so they use iron for this particular process. So this is an achievement in catalysis at that time, even today. This is an achievement in catalysis at that time, 100 years back, even today this is an achievement. Next achievement is to find a catalyst or the same catalyst, do this at low temperature and low pressures, ambient conditions. That is the next step that we have to achieve. Okay? So these are the three gentlemen, Haber, all of them received Nobel Prizes, all three of them, for this particular process. Okay? The important point here is, in the NN bond is a triple bond, it is very, very inert molecule. You need to break this NN triple bond. Your ammonia and nitrogen, the triple bond has to be broken, then you have nitrogen, it should form bond with hydrogen. So breaking this bond requires 1500 Kelvin, that is about 1200 degrees, 1300 degrees centigrade, only it will break. But when you use ammonia, iron as a catalyst, this can be broken even at 80 Kelvin. Even at 80 Kelvin. 80 Kelvin. Okay? Yeah, over 90 Kelvin, yeah. Okay? So that is what actually the people have investigated, and then finally found out that active sites for breaking this, for this ammonia synthesis, C4 and C7, I'll show you in the next. So to study these processes, people use XPS, which I talked about yesterday, ultraviolet photoemission spectroscopy, high electron energy loss spectroscopy, low energy electron diffraction. Some of these techniques they use to study the, scientifically to study this process. Okay, what is the result? The result is, when they use this Fe111 plane, Fe100, Fe110, they studied the amount of coverage of nitrogen atoms in the y-axis here, the coverage of nitrogen atoms, chemabsorbed at 693 Kelvin on single crystal surfaces exposed to nitrogen. What they have done, they took iron, single crystal, with 110 plane. You can cut the crystal, you can grow the crystal, cut the crystal in 110 plane, 111 plane and 100 plane. That is possible. Take that crystal, expose it to nitrogen under certain conditions. What they found is that 111 plane has strong affinity for nitrogen atoms. You see, immediately the moment nitrogen is exposed, immediately it forms the coverage shoots up very, very high. Whereas in this case, the coverage also shoots up, but it takes time. It requires higher nitrogen exposure. Whereas in this case, it is very slow, 110, which means which plane is more reactive, which plane is more active for the nitrogen absorption? 1111 plane, right? So if I have a catalyst with iron particles containing 111 plane, then that will be more active. That is the conclusion, right? Now look at the next one. That's what exactly they found here. Ammonia production, nitrogen absorption, ammonia production. Ammonia production is very high in the case of Fe111 plane. Fe111 plane. So this is possible. These things were not possible at that time when it was invented. But now it is possible to study all these and then exactly pinpoint which plane is responsible for higher activity. So here you have ammonia production is very high. In this case also ammonia production is there, but it is not as high as it is. Fe110 activity is there, but it is very low. Now the sites actually, what are the sites which are responsible for that? See, if you see this 111 plane, there is a site called C7 site. This is C7 site. That is coordination number 7. That atom has coordination 7. So those sites, if you have, that is plane is going to be very active for ammonia synthesis. Okay, so those kind of planes are present in these planes, C4 and C8, C6 and C8, right? So C4 and C7 sites are are responsible for ammonia production. So these are all cannot be seen with naked eye, but you can see today it is possible to see surface, how atoms are arranged, which atomic arrangement is more stable, which atomic arrangement is more active for adsorption, which atomic arrangement is more reactive, catalytically active plane. That these things are all possible. Okay, so same thing here. Fe111 plane shows reaction rate is very, very high. Fe100 plane reactivity is somewhat less, and Fe110 reactivity is very, very, very small. Okay, so that is the reason why we need to study surfaces and chemical process at surfaces to point out, to understand all these finer details at atomic and molecular level. Okay, we break a little bit or? Huh? What time is it? 10:30. All of 1.5 hours is over. Huh? Huh? After 10:50 you are going, you have something else, is it? Next class will have. Okay. All right, I have shown you all these things earlier. These are different species which are present on the surface, Ithridine surface. These are all well characterized. These are all well characterized using different surface techniques. Okay. Next one I just want to quickly recall is Langmuir isotherm, adsorption. For example, fractional coverage, adsorption is a process where molecule is called adsorbate and surface is called adsorbent. Okay, adsorbent. Okay, all right. So you can have a dissociative adsorption or associative adsorption. Associative adsorption is molecule adsorbs on surface from the gas without any fragmentation. It adsorbs as it is. So then it is associative. Suppose if it dissociates into fragments, then we call it as dissociative adsorption. Dissociative adsorption. Okay. Some of these concepts are discussed in Atkins Physical Chemistry 8th or 9th edition, or even later editions also. Develop a habit of reading textbook. Develop a habit of reading textbook. Notes is fine, but still you should have a textbook and read that. The topic when it is discussed in the class, go back and look at the textbook also. Okay. So now adsorption phenomenon was first studied by Langmuir. Who is Langmuir? One of the Nobel laureate. He published this paper, the adsorption of gases on plane surfaces of glass, mica and platinum. This was published in 1918 in Journal of American Chemical Society. Today there is a journal called Langmuir. There is a journal named after Langmuir. Publishing in Langmuir is very difficult. So I wish all of you join PhD and everybody publish papers in Langmuir. Yes. Okay. So this is we have published one recently. This is my name. 2023. And there are quite a few of our department colleagues published papers in Langmuir. So this Langmuir is a very popular journal. This is the name comes from the Irving Langmuir, who actually did a lot of work in surface chemistry, in surface processes, well 100 years back. Okay. So that is a Langmuir isotherm we are still studying even today. Okay. Postulates of Langmuir isotherm. This was formulated by Langmuir in 1916. He says all adsorption sites are fixed, electrically equivalent. no lateral interaction between adsorbate molecules, adsorption restricted to a monolayer, at equilibrium rate of adsorption is equal to rate of desorption. He actually took all these 4 assumptions. These are assumptions, all are wrong. Right? Why they are wrong? All adsorption sites are fixed and energetically equivalent. Just now we saw, right, different sites, bridge sites, 4-fold, 3-fold, they are not same. But they didn't have all these techniques to see all that at that time, 100 years back. Right? Now we know, because we have all the techniques, so we see, oh, this is different, this is different. There is no lateral interaction between the adsorbate molecules. That is also wrong. Because the 2 molecules sit together, close to each other, they repel or attract because of the intermolecular forces. Right? So that is also not correct. Adsorption restricted to a monolayer, that is somewhat correct. Okay. But that is also not entirely correct. The multilayer is possible. Multilayer is possible. At equilibrium, rate of adsorption equal to rate of desorption. That's okay. That's fine. If it is a monolayer, monolayer is possible, multilayer is also possible, but there can be adsorption, desorption. There is equilibrium between. That is, these are the postulates. These are the things he said, okay, let me start with these 4 and move on. He went ahead and derived the Langmuir isotherm, which says that equilibrium constant, for example, we have a site, a molecule in the gas phase molecule adsorbs on that, gives you SM. SM is the molecule sitting on a site, right? So equilibrium constant is equal to the concentration of this divided by concentration of this and that. Okay? This is a straightforward one, right? And then this SM, that is a molecule which is sitting on the surface, occupying the surface, is proportional to the surface coverage. That is theta. Okay? Proportional to theta. Now, vacant sites are proportional to the number of vacant sites. That is proportional to 1 minus theta. Theta is the number of sites occupied. 1 minus theta is the number of unoccupied sites. Okay? So, this concentration is proportional to 1 minus theta. M is proportional to the pressure of the gas. If you are talking about gas interface, gas solid interface system. If you can also look at solid liquid interface. In that case, the P becomes concentration. P becomes concentration. Okay, you must have studied this charcoal adsorption on acetic acid adsorption on charcoal experiment. Have you done that in your no? Yeah, there is an experiment. So the rate of adsorption is d theta by dt is proportional to pressure times number of molecules hitting 1 minus theta. You are all familiar with this, right? How many of you are familiar with this? Langmuir isotherm? The derivation. Some of you, not all of them. Anyway, let's go through that. So rate of adsorption is proportional to the number of sites available. Number of sites available, vacant sites. So the rate of adsorption is how many molecules will go and sit in those sites, right? So that should be pressure times the number of molecules hitting under 1 minus theta. And rate of desorption is proportional to, suppose a number of molecules are sitting already, they are the ones which should dissolve. So that should be equal to theta. So rate of desorption is proportional to theta, of course proportionality constant is K, and then number of molecules that is dissolving. So at equilibrium, these rates should be equal. These 2 rates should be equal. Correct? So many molecules are adsorbing, so many molecules are dissolving. So this rate should be equal at equilibrium. So you equate these 2, then you end up getting 1 theta by 1 minus theta is equal to Ka by Kd times P. Okay? You are actually equating these 2 and then you get this one. From this you can find out B. This B is nothing but this Ka by Kd is given as B. So the B is equal to theta by 1 minus theta times P, and this the unit for this is atmosphere pressure to the power of -1. Pressure to the power of -1. Okay. So this is the kind of Langmuir isotherm, Langmuir expression isotherm. For non-dissociative chemabsorption molecules, molecules are not dissociating, they go and sit and then come out. And for that particular system, theta is equal to Bp by 1 plus Bp. P is the pressure, B is nothing but K adsorption by K desorption. Now this B is very important. If K adsorption is more, B is more. Right? If B is more, adsorption is faster and quicker. Okay? I'll show you that. Here it is. Now this is the expression that we have. Now if you see coverage, if you plot coverage, that is theta, and then pressure here, this is pressure. Now you start seeing, as you increase the pressure, you start seeing the adsorption, coverage increasing, and here surface is covered very sparsely. That means, now there are a lot of vacant sites available, so adsorption is taking place. Whereas, when you go to higher pressure, it is almost getting covered. This process is, this phenomenon is similar to enzyme catalysis. You are all familiar with enzyme catalysis? It is similar to that. You just go and compare these two. It is similar to enzyme catalysis. Enzyme catalysis also is an enzyme, there are sites, the substrate will go and sit on that and it gets saturated. So it will also give you this kind of a curve. If you see carefully, go compare these two, right? So then what we can do is we can actually plot 1 by theta versus 1 by p. You can plot. That will give you a straight line. That will give you a straight line. Where is that? Or in other words, at low pressures in this region, at low pressures, this value p is small. So this Bp can be much smaller compared to 1. You can ignore that. If you ignore that, your theta is going to be equal to Bp. So it is linear. Coverage versus pressure is linear here. You see, this is linear. Linear portion, right? At high pressures, the P is more, the P is large, so you cannot ignore that. So this is going to be greater than 1, right? So you can ignore 1 here. If you ignore 1, these two will get cancelled. Theta is going to be close to equal to 1. So this coverage, this theta is going to be equal to 1 in this region. It starts from 0 and it ends up at 1. It varies between 0 to 1. 0 to 1. Okay? So you can actually rewrite this expression, and then can you rewrite this expression and then 1 by theta? Can you rewrite this expression? You reverse it. Inverse it. Reverse it. Take 1 by theta, so you can get 1 by theta versus 1 by p. What did you get? Huh?
1 by.
So 1 by theta is equal to 1 by. So you have to plot 1 by theta versus 1 by p. 1 by theta versus 1 by p. The root p is for a dissociative adsorption. That we will not worry about it now. So 1 by theta versus 1 by p, if you plot, what should you get? You get a straight line. You get a straight line from the slope and intercept. You can calculate the b value. Yeah, what is the slope? Right? All of you got it? All right. So that's how you can calculate the b value. Okay? Here it is. So you can 1 by p versus 1 by theta if you plot for oxygen, carbon monoxide, etc. At different temperatures also one can do experiment at different temperatures. But the entire experiment should be the same temperature. Isotherm means the experiment should be done the same temperature. Right? So, this isotherm at 373K, 273K and 273K, if you see, these are all showing straight line. So, this is the intercept, and then slope will give you 1 by B is your slope. From there B can be calculated. So, this is Langmuir isotherm. Okay. Now, this B is only constant if enthalpy of adsorption is independent of coverage. The B is constant only if enthalpy of adsorption is independent of coverage. Independent of coverage. That means that as you increase the coverage, right? So the molecules, what they will do, the molecule will go and first, will sit in the sites where enthalpy is high, where they are more comfortable, and then they start occupying the next sites, and they occupy the next sites where the enthalpy may not be very high, because these are all not homogeneous, heterogeneous. This surface is heterogeneous. It doesn't have, all the sites are not equal. Some sites are highly attractive in terms of energetically they are very attractive. Some of them are not. They are heterogeneous. So delta H is not same for all of them. So if you want to find out the delta H, you have to fix the coverage. At that coverage, what is the enthalpy? You change the coverage, you will have a different enthalpy. Right? See, all of you are sitting here. Some of you may prefer to sit in this front benches. Some of you may prefer to sit back benches. Right? So these are all different sides. There is red and there is blue. Right? Okay. So with that, with all chemical equilibrium, the value of B will depend on the number of factors. One is that the stability of the adsorbed gas molecules involved, and temperature of the system, and then pressure of the gas above the surface. These are all some of the things which influence that. So what we can actually do is, if you see here, suppose say if B is large, what is B? K adsorption divided by K desorption. That is the definition. K adsorption is very high, means adsorption is more favorable. Even at low pressures, the adsorption will be very high. So that's what is seen here. See, the B3 is very large, so immediately, even at low pressures, it starts filling up the sites. Whereas B2 is smaller than that, you can see this taking little longer time, whereas B1 is taking little much longer time, much larger pressure to complete the full coverage. Okay, all right. So the B value has a lot of influence. Always remember K adsorption by K desorption. If K adsorption is high, means adsorption is favorable. So what people do, for example, you wanted to calculate the delta H, for example. If you are, suppose say if you see, you have done an experiment where different isotherms are recorded here. Okay, and these are the different isotherms. Increasing delta H. Delta H is increasing, that means B is also increasing. Delta H is increasing means B is increasing. Delta H is increasing means higher the delta H, that is more negative the delta H, adsorption is increasing, is favorable. So B is favorable. B is favorable, right? So as you increase the H value, the coverage is increasing very sharply even at low pressures. Whereas in this particular case, now, so what you do here, you plot you take a line, for example, you want to calculate delta H value at a particular coverage, 0.3, then you plot a line here, and at each point where it is touching this isotherm, you record the pressure, record the coverage is fixed, pressure is, you can record. Isotherm means, you know the temperature of this. Each isotherm, when it is recorded, temperature is known to you, and the pressure is known to you. So you take those readings and plot and plot 1 by T versus LNP. You make a plot that will give you a straight line. That straight line gives you delta H value. This is nothing but our Clausius-Clapeyron equation. Clausius-Clapeyron equation says dLNP by dt is equal to delta H vaporization divided by RT square. Right? So this expression, since in this plot, LNP versus 1 by T gives you minus delta H by R. That comes from Clausius-Clapeyron equation. So now remember this P values and T values that we have taken at a constant theta here. At constant theta we have recorded this P and then temperature. Correct? So you are getting actually these values at constant theta. So this is called isosteric heat of adsorption. The delta H that you calculate, the slope of this is delta H by R. So from that you can get delta H. This delta H is nothing but isosteric heat of adsorption. Isosteric heat of adsorption means adsorption calculated at a fixed coverage. At a fixed coverage. Okay? So that's how this is calculated. Yeah, so this is basically the derivation of that. Dou LNP by dou 1 by T is equal to delta H by R. How do you get that? So this is the derivation of that, starting from Langmuir isotherm. See, all that you are doing is this B, you are now equating it to equilibrium constant. It's the equilibrium constant basically, right? So replace B with K and then take Ln and then find out the derivative of that and use Van der Waals equation. You end up getting this expression. Okay, that you do it as an exercise at home. Okay. I think this is given in Atkins' book, 9th edition, page 891. Probably I have given a reference there. So if you have any doubt, you can call that. You want to write everything? Write the last one. You have to start from this, and then you have to replace B with K because B is nothing but equilibrium constant. You can replace it with equilibrium constant, right? And then take a ln of that, and then derivative of that. From that, use Van der Waals equation, so that you equate this with using a Van der Waals equation. So you get delta H by RT square. The T square can be absorbed in the derivative here. So then you get this value correctly, and that's exactly what you are measuring experimentally in the isotherm experiment. Okay, all right. Okay. Of course, I told you there are limitations of Langmuir isotherm. I have given you already. Right? These are all some of the limitations which I already said initially itself. The postulate itself, there are some, but they of course there was no way for them to. But still, I tell you, there's something called ideal gas equation. What is the ideal gas equation? Is it correct? It's not correct. There is no ideal gas, right? You under certain conditions it behaves ideally. Otherwise, there is no ideal gas. No ideal gas, no ideal liquid, no ideal solid. You have? Right? No ideal universe also. Why? Entropy of universe is increasing. This is not ideal. Entropy is randomness. Ideal cannot have randomness. It should be ideal. Right? So, under certain conditions, this ideal equations are valid. So this is also one of the, in this area, you can call a Langmuir isotherm is an ideal equation. Okay, all right. You can still apply it under certain conditions. Okay, so I think I will stop here maybe. And this Langmuir isotherm can be applied to study the rate of reactions on surfaces. Unimolecular reactions, bimolecular reactions, that will take another half an hour. So I will stop here. Okay, all right. So with that, I'll just quickly, of course, BET isotherm is there. BET isotherm, this is a derivation. I am not too sure that this will go above BET isotherm. We will not worry about that. And this application, etc. So I will stop here. But interestingly, all this absorption experiment that you are talking about, we have a nice experiment in equipment in our department, in the ground floor of this building, and there is one new one has been bought in the other building, the adjacent building. Go and have a look at it. Are you taking them? Yeah, so have a look at them. This is an older one, but new version has come. New thing has been installed there. This is the older version. This is the version to study BET isotherms when we were students. We used to sit in front of the glass, these panels, and then, start putting the sample here, do all these things, finally, this is how it used to be. We used to do it manually, sit there for about 5, 6, 7 hours and do the experiment, measure the surface area, right? But today, if we ask you to do it, you will quit, you will not do research, right? So today everything is mechanized. You just put the sample there, into 1 hour you degas it and then leave it there, it will give you the result. This is the surface area. How do you get that surface area is something which I wanted to explain to you. This is how you should get your surface area. Where is that? Here. Yeah. So this is a BET experiment from which you should be able to calculate this BET surface area. All this mathematics is already programmed in the machine, and it will give you the result. It will give you the result. That is the theory behind that. This will take another 1 hour, so we'll stop here. Okay, all right.
SwayamPrabha, Digital India, Educated India.